I want to thank Anton for inviting me to give this course of lectures. It's a great pleasure to visit this famous department. I've known many fine mathematicians who are graduates of Leningrad or Petersburg State University over several decades, and it's nice that I have the opportunity actually to come here finally. So I want to talk about functional models for pairs of contractions. But I thought it wouldn't be reasonable to assume that everybody was completely familiar with the Nagy-Foias theory for a single contraction. And although there are people in this room who know much more than I do about that, I think I have to go through that at least briefly, insofar as is possible in one lecture. So the idea of a canonical model for operators, one would like to present some fairly concrete class of operators which in some sense represent all operators. Of course, that's a very ambitious goal to set oneself, because our operators are such very different things. Integral operators and multiplication operators and composition operators. Why should one expect them to be describable under a single kind of format? Nevertheless, there was some progress made in this ambitious project going back quite a long time. So there's Lifshitz and Brodsky, I think probably the 1950s, and then de Branche and Rovniak, a similar time, maybe slightly later, and then the one that I'm going to concentrate on, Nagy and Foias, who wrote a rather wonderful book called The Harmonic Analysis of Operators on Hilbert Space. And this came out in the original edition was in French in 1966, and then there is an English version that came out in 1970. And this is what I'm going to be talking about in this lecture. So what is a canonical model then? Well, if you think back to the canonical forms that one learns in linear algebra, there are some very good canonical forms, like for example the Jordan form for matrices under similarity, which is a very powerful tool which enables us to answer a lot of questions rather simply. But a notable example of something that's missing, there isn't really a good canonical form for matrices under unitary equivalence, even in finite dimensions. But nevertheless, that's what we want to do. We want to have something like a Jordan form, except with respect to unitary equivalence and for operators on infinite dimensional Hilbert spaces. So that's a really very tall order. It's rather remarkable that one can say anything at all about it. But that's what this book is about. So let me describe some of the basic objects. I think maybe I'll put it on that other board. I see there's a trick to this, isn't there? I'll tell you what, I'll do it on this one. I'll rub this up. So some basic objects that we're going to be using. Suppose E is a separable Hilbert space. Then L2E, that just means, is going to mean measurable E-valued functions, square integral measurable E-valued functions on the circle. So this is the set of F going from the circle, the unit circle, into the Hilbert space E. F measurable, and of course the norm of F, which is defined to be norm F squared, integral of the circle F of e to the IT. So F of e to the IT is an element of E, and that's got to be finite, of course. So I'm sure this is an extremely familiar object, and we know that this is more or less the same as L2Z of E, which is defined to be the set of square summable sequences. So you have something like, let's say, A minus 1, A0, A1, where AJ is in E, and the sum of norm AJ squared is finite. And then H2 of E is going to be just what you expect. So that's the functions from the disk into E, which are analytic, and sup less than 1 of the integral. So that and this, of course, is more or less the same thing as L2Z plus of E. So it's similar to this one, only you start at 0. So A0, well, just the sequence of Taylor coefficients, such that sigma norm AJ squared is finite. I'm sure this is familiar to most of you. And then we're interested in some operators. So there's the bilateral shift, on L2 of E. And I'm going to write that as M sub Z, so multiplication by Z. So M sub Z, if you think of it acting on the sequence of Fourier coefficients, A minus 1, A0, or maybe it's not a good way to define it. M sub Z of F at Z is equal to ZF of Z. And of course that's, when you think of it with this description of L2, then of course that just means shifting.
So how does big L2 and little L2 correspond to each other exactly?
Well, these are the Fourier coefficients. So if you've got Yeah, well, with respect to the trigonometric basis. So if you take a function f in L2 of E, then you can write its Fourier series as sigma ak e to the ikt, where ak is in E. K equals 0 to infinity. So that's f of e to the it. Yeah, minus infinity. And so these are just the ordinary classical Fourier coefficients of the function f. Okay. And then there's the unilateral shift. On H2 of E, and I'm going to write that as T sub Z. It's often written as capital S, but I want to use capital S for something else later. So this is the Toeplitz operator with symbol Z, which is this. So T sub Z acting on F Z is equal to Z F of Z. So formally the same as the bilateral shift, but of course here, if you think of it in terms of the sequence of Taylor coefficients, that's also shifting one place to the right. Tz shifts, so Tz maps the sequence A0, A1, A2, etc. to 0, A0, A1. And so we also will need their adjoints. So the adjoint mz star f at z is just going to be z bar f of z. And tz star f of z. So that's the projection onto H2 of z bar f of z. And that turns out to be f of 1 over z times f of z minus f of 0. So that's the backward shift on H2. This is a unilateral backward shift. So anyway, those are some of the objects that we're going to be using in order to model contractions. So now let me say a bit about contractions. So a contraction, that is an operator T on a Hilbert space, let's say H, such that norm T is less than or equal to 1. And so T is a contraction if and only if 1 minus T star T is positive, and that's because the norm of an operator is equal to the norm of its adjoint. That's the same as 1 minus tt star greater than or equal to 0. And because positive operators have square roots, we can define the defect operators. These are going to be very important. So d sub t is the square root of this positive operator, 1 minus t star t to the 1/2. And so, of course, the defect operator of t star is 1 minus tt star to the 1/2. And we also have the defect spaces. So script d sub t is just going to be the closure of the range of d sub t. And of course d sub t star is that. So I'm afraid there's no way out of giving rather a lot of rather dry definitions in order to introduce this subject. And one important thing to notice is the following. If you look at t times 1 minus t star t, that's the same as 1 minus t star times t, as you can instantly see. And in fact, if you just think of you can just put half there and it's still true, because this, you can approximate it by polynomials in t star t, and then the equation that I had before will work for each of those approximating polynomials, and so in the limit you get this. So that says t d sub t is equal to d sub t star times t, and therefore if you apply this to a general vector, you get t sub d sub t is contained in d sub t star. So that's quite an important relation. Right, that kind of sets things up. I think maybe those last equations need to be in view, those last definitions, and I can use this board. I'm just wondering if I should use that board.
I don't know these slides.
Well, if I need to use slides later, I can always pull it down, presumably. Can I just push that up with this? How does that work? Oh, great. Yeah. Excellent.
That's the usual story here. Don't worry about that.
Right, so the goal is to start with a pretty well arbitrary contractive operator on Hilbert space and somehow express it in terms of these objects which we assume to be familiar. So if they're not familiar, then of course it's a bit more of an obstacle, but I guess most people here will have met these objects. So how can we do that? Well, there is a special case of contractions in which this can all be done in a fairly elementary way. So I want to describe an embedding. Of H. So I'm assuming, as before, that we've got, as up there, that we have a contraction T on the Hilbert space H, and I want to embed H in an H2 space. So that's the first step, really. And here's how we do it. I'm going to define an operator W. So we define W from H into H2 of D T star in the following way. For X in H, we define Wx, it's got to be an element of H2. And as I said, we can think of H2 if we want in terms of the sequence of Taylor coefficients as on in this line here. So it's going to be the following: dt star of x, dt star t star of x, dt star t star squared x, and so on. So just with increasing powers of t star. And of course one has to check that the norm, the sum of the squares of the norms of these objects is finite, but we can do that quite easily, because let's think what norm of wx squared is. Well, it's norm of just the norm, sum of the squares of the norms of these Taylor coefficients. And that's by the definition of the norm like that. But norm of dt star x, that's so that's dt star x comma dt star x in H, etc. And then we take this dt star over to the other side and we get dt star squared, and so that's 1 minus t star x comma x. And then the same thing with x replaced by t star x, so that's 1 minus t star x, and so on. And so this, of course, is just norm x squared minus norm t star x squared here, just expanding that in a product there. And then this one will be norm t star x squared minus norm t star squared x squared. And the next one will be norm t star x squared plus, t star squared x squared minus norm t star cubed x squared, and so on. And so this is a telescoping series, and so you get left here with norm x squared. And then if you sum the first n terms, you get minus norm t star to the n x squared. But then we have to let n tend to infinity, so it's that. And the point is it's less than or equal to x, whatever happens about for any contraction t, this limit. And so this is finite. So norm of wx squared, norm of wx squared is less than or equal to norm x squared. So w defined in this way is a contraction. Now, if we are sufficiently lucky that t star to the n tends to 0 strongly, then this limit will be 0. So let's define t is a pure contraction if t star to the n tends to 0 strongly as n tends to infinity. So do feel at liberty to ask any questions, for me to clarify things if you want me to. Yeah, I'm possibly going too slowly for many of you, but I think that's the lesser evil than going too fast. So you can see from this formula here that if T is a pure contraction, then W is actually an isometry. In other words, norm of Wx is equal to norm of x for all x in this case. So we have now an embedding of H. Let's just stick to the pure case now. So assume that T is pure. So we have an isometric embedding of H into H2 of dt star, the defect space dt star. And there is a simple intertwining relation that we can see here. Suppose we look at Wt star applied to x. Well, according to the formula at the top of the board there, that's d sub t star of x, d sub t star squared x, and so on. But then if you compare that with Wx, that's just the same as Wx, except shifted one place to the left. And so that's the same as saying that it's the backward shift. So the backward shift I'm denoting by Tz star. It's the backward shift applied to dt star x, dt star t star x, and so on. And that's T, the backward shift applied to W of x. So W intertwines the adjoint of T and the backward shift operator on H2. And so we can almost immediately get a really cheap functional model just from this rather simple observation here. So let me one thing that follows from this is that the range of W is invariant under the backward shift. Because anything in the range of W is of this form. If you apply the backward shift to it, then you get something which is in the range of W. So let's call that E. That E be the range of W, which is contained in H2 of dt star. Then it's invariant and so we have a small theorem I'll write it here. I'll leave W in view, it's not so central. Well, this is so simple it hardly deserves to be called a theorem, but I will call it a theorem anyway. And so it just says the following. If T is a pure contraction, then T is unitarily equivalent. I'll use this symbol for unitary equivalence to the backward shift restricted to E for some backward shift invariant subspace E of H2 dt star. So I guess this is something that people noticed going back a very long way, and I guess that was more or less the starting point for the Nagy-Foias model theory. Of course, it's not much of a theorem so far, because unless you actually know what script E looks like, unless you have some concrete description of it, then really it's no use. But Nagy-Foias managed to give a very beautiful description of E. So that's the next thing I want to describe. They discovered or introduced something called the characteristic operator function. Of T. So T, remember, is just a contraction on H. At the moment, I'm not going to assume that it's a pure contraction. It's just any old contraction. Then capital theta sub T of lambda. First of all, I'll write it down, then I'll say what kind of object it is. So that's going to be minus T plus lambda d sub T star 1 minus lambda T star inverse d sub T. So you can see that's an operator. Well, I better say what lambda is. So for lambda in the open unit disk, T is a contraction, so 1 minus lambda T star has a bounded inverse, and so this is a perfectly good operator on H, and this is going to be restricted to d sub T. So we start in d sub T, you apply d sub T, your vector in d sub T, you apply this defect operator, you stay in d sub T, you apply this bounded operator, this 1 minus lambda T star inverse is a bounded linear operator on H, and so you get something in H, you apply d sub T star, that will give you something in script d sub T star, and the defect space script d sub T star. And so this is an operator from d sub T to d sub T star. So for each lambda in the open unit disk, that's a well-defined operator. And so theta sub T is called the characteristic operator function of T, and it's an analytic, so theta sub T is an analytic operator valued function on the disk, and it's contractive. So for each lambda, the operator that you get, theta sub t of lambda, is a contraction, and in fact it's what's called purely contractive. So not only is it a contraction, but it has the property that if you apply theta sub t at 0 to any vector x, that's strictly less than the norm of x for any x in d sub t. So with the contraction t, we associate this purely contractive analytic operator valued function. Now, so far it's probably not clear what good that's going to do us, but the point is that we can describe the range of W. So we remember what we're trying to do is give a concrete description of this space E, which is the range of W. W is the embedding of our initial Hilbert space H into this H2 space, this Hardy space, and we would like to be able to give it a nice description. Well, in fact, Nagy-Foias were able to give that promised description in terms of theta sub t in the following way. So there's a beautiful identity. It says the following. WW star plus M sub theta sub t, I haven't said what that is, but I will in a second, is equal to the identity on H2 of dt star. So here I'm once again assuming that T is a pure contraction, so the powers of T star tend to 0 strongly. M theta sub t is just a multiplication. So M sub theta sub t goes from H2 of dt star in the following way, just the obvious thing, M sub pointwise multiplication. If you have a function f in H2, then the pointwise multiplication is like that. Multiplication operator. So I guess we have a break about now, do we?
Yes.
Is that normal? So I would like to prove this, but maybe I should do that after the break.
Good.
Right, I will continue. So just to recapitulate, we have a contractive operator T on a Hilbert space H, and we're going to try and express it in terms of some familiar objects, the shift operator on H2, a vector valued Hardy space. And we've got part of the way from this theorem up here, at least for pure contractions. So contractions for which the powers of the adjoint tend strongly to 0. And so this little theorem says that any contraction, any pure contraction T is unitarily equivalent to the restriction of the backward shift to some invariant subspace script E. And in fact, script E is the range of this operator W up here. So E is the range of W. And so our immediate goal is to describe the range of W in some nice concrete way. And in fact, we can do that using this slightly mysterious object, the characteristic operator function of T. And so we're going to use this identity, which I have just written down, and I'm intending to prove that. But before I do, let me just say what the conclusion will be. So we're going. The proposition is that the range of W, still in the pure case, the range of W is H2 of dt star, orthogonal complement theta sub t H2 of dt. So I hope it's clear what this means. For each lambda, so theta sub t, this is just theta sub t of f in H2 d sub t. And so it's the range of this operator m sub theta sub t here. And so if we put this observation together with that little theorem, then we get a slightly bigger theorem, but still quite small, that says that if T is a pure contraction, then T is unitarily equivalent to well, let me write it down. If T is a pure contraction, then T is unitarily equivalent to the compression of the forward shift to H2 dt star orthogonal complement theta sub t H2 of d sub t. And that is already a decent theorem, because we have a very general object, a pure contraction, and we say that it's equivalent, that it's unitarily equivalent to the compression of the forward shift, which is a very much studied and fairly well understood operator on H2, to an invariant subspace of the backward shift.
I'm sorry, but maybe this could. The star disappears from.
Yeah, I was slightly worried about that. Yes. So where should there be a star then? Should it be?
It's a proof. It was. I didn't mark it because when you prove, you apply T star to the vector x.
Yeah.
Because then you got a shift.
So this should be a T star up here.
Yes.
And then here we've taken the adjoint. So this is actually correct. This one is correct. The other one was not quite correct. Yes. Right, so what we need to do in order to obtain this theorem is to prove this identity here. So let me try and do that. So I want to prove this. So first I better work out what W star is. So let's look at, so W star goes from H2 into script H, into our original Hilbert space. So let's consider W star on some typical element of H2. Well, I wouldn't write down a completely general one, but I can write down a fairly typical sort of element. Right, so so what does that mean? So K is the Sago kernel. So Kw of Z is 1 over 1 minus W bar Z. And this is the reproducing kernel for H2. And if I take a vector y, so let me say for W, little w, in the disk, and y in this space, defect space dt star, then this is the element, so Kw tensor y in H2 dt star just means the obvious thing. It means that it's the function whose value at a point lambda, say, is Kw of lambda y. So the fact that this is the reproducing kernel, what does that mean? So it means that if you have any function f in H2 dt star, and you take, it's in a product with the reproducing kernel, so that's in the inner product in H2, then that is just f of w. So because f is in H2 of dt star, this is a vector in dt star. So that makes perfectly good sense. And of course that's the same as f of w y in the original vector space, Hilbert space H. Right, so I'm going to work out what W star does to the reproducing kernel. So let's take its inner product. So this will be in script H. So let me take its inner product with a vector x in H. And of course that is the same as Kw composed with y in a product Wx. And this, of course, is in H2 dt star. And Wx, well, Wx is written at the top of the right-hand board there. So that's the same as Kw tensor y. Now let me write that down so I've written down the sequence of Taylor coefficients for Wx, but if I want to write it as a function of z, the variable z, then that is just dt star 1 minus zt star inverse x. So that's a slight abuse of notation there, but this means that the function of z, whose value at z is this quantity. So this is a function, and so it makes sense to talk about this is a function in H2 dt star. And then by what I've just said about reproducing kernels here, that is going to be, you just substitute w for z in here. So you just get dt star 1 minus wt star inverse x in H. And then I can rub this out because we've used that. And I can bring these operators over to the other side, and so that will be 1 minus w bar t inverse d sub t star y in a product x in H. And now if you compare this with this, that's true for all x in H, and so we conclude that w star applied to the reproducing kernel k sub w tensor y is this object, 1 minus w bar t inverse d sub t star y. And so now we can write down w star applied to k w tensor y. So this w star goes from H2 to H2. And so this whole object will be an element of H2. And so we can work out what its value is at the point Z. So it's the same as w, so that's w applied to this thing that we've just worked out. 1 minus w bar t inverse d t star y. And we want its value at z. And then once again by the formula for w up there, that's equal to d sub t star 1 minus z t star inverse times this quantity 1 minus w bar t inverse d sub t star. Yeah, I think that's right. Right, so we now know what w star does on the reproducing kernel. And I'm trying to prove this identity at the top of the board, and so I need to work out what m theta t star does to the reproducing kernel, and I hope that when I add them up I will get the identity. That's the plan. Right, so the next step is to find out what m theta t star does to a reproducing kernel. So I take a w in the disk and a y in dt star. And I want to work out what that is. So let's So this will be, so this is a function in H2 of dt star, but we're multiplying it by theta, so we'll get something in H, I got my stars wrong again. Oh yeah, this is right, H2 dt star. Yeah, so that will be kW tensor y. And then I move this over here, and multiplication by theta sub t, so it's theta sub t f. And that will be in H2 of d sub t. And now by the properties of the reproducing kernel, that's the same as y in a product. And then we just take the value of this function at w. So that's theta sub t of w, f of w, and that's in d sub t. A defect space. Or should it be in d sub t star? I'm slightly concerned about my stars. Well, let's see.
No, this is in d sub t star. F in d sub t. And
Yeah,
the result is
that's right. Yeah, y is in d sub t star. Yeah, of course. Right. Thank you. And so this is theta sub t of w star y f of w. And this time I think it is in d sub t.
no, it's something wrong.
Is there?
There has to be d sub t star, here d sub t.
Oh dear.
Yeah.
So let's see. This is a function in H2 of d sub t star. Yeah, no, it should have been d sub t, shouldn't it? Yeah. Oh dear. But then this will be, so this is correct. This one's correct.
No, to apply f, f has to be in d sub t. Yeah?
F is in, oh yeah, you're right. So that's right.
And after the result will be in d sub t star. So in the next,
So this one should be d sub t star then, should it?
yeah.
Ah, well. So this is correct,
Yeah.
and then this is correct, I think. All right. And now, once again, using the property of the reproducing kernel, this is the same as kW tensor product theta sub t of w star y f in H2 of d sub t. So the conclusion is that m sub theta sub t star applied to the reproducing kernel, kW tensor y, is kW tensor theta sub t of w star y. And so if we now look at m sub theta t times m sub theta t star. So this is what we're interested in. We're trying to prove this identity up here. So we want to know what m sub theta t, m sub theta t star does on H2 of dt star. And we can do that now, because this, so if we take this, if we apply this to a reproducing kernel kW tensor y, and we look at its value at the point z, what's that going to be? Well, first of all, multiplication by theta sub t, we're just going to have a factor theta sub t of z. And then this object, m sub theta t star kw tensor y, we've just worked out what that is in the line above. So it's this evaluated at the point z. And the way you evaluate this at the point z is just kw of z times theta t of w star y. So what's that? Well, kw of z is just 1 over 1 minus w bar z, so it's 1 over 1 minus w bar z, theta t of z, theta t of w star y. So now we worked out ww star, it's here, and we've worked out m theta t star over there. So we just need to put those two things together and hope that we get the identity. So it's enough to prove that you get the identity operator on the reproducing kernel. Clearly, if you have an operator, because the reproducing kernels span a dense subspace of H2. And so if it acts as the identity on all the reproducing kernels, then it will be the identity operator. So let's look at ww star plus m theta t star applied to kw tensor y. So it's, according to this, it's dt, the first term is dt star 1 minus zt star inverse 1 minus w bar t inverse dt star.
Y. Thanks, Y.
Y, thank you. Yeah, so there should have been a y down here, shouldn't there? And then from the right hand board, that's 1 over 1 minus w bar z theta t of z theta t of w star y. Now we're almost there, but we need one more ingredient, and this is an exercise. And it's a rather beautiful identity. 1 minus theta sub t of z theta sub t of w star equals 1 minus w bar z times d sub t star 1 minus zt star inverse 1 minus w bar t inverse d sub t dt star. So if you haven't seen this kind of thing before, it's worth doing this exercise because it's very pretty. It's rather a beautiful little piece of algebra. I mean, it's quite elementary, but it's the kind of thing that crops up all the time in this area. And so now if you combine this with this, so let's see. So coming on from here, let's take out 1 over 1 minus w bar z dt star. Oh, well, that's, yeah, we'll just take out 1 over 1. So then this term gives us 1 minus w bar z dt. I don't know whether I really need to go into the gory details here. You can probably all see immediately that it's going to give us the identity. Right, that's this term. I've just taken out 1 minus. And then over here, so you get that, but then we've just said that this here is 1 minus theta t of w bar, theta t of z, theta t of w star. And so these two cancel, and so you just get 1 over 1 minus w bar z times y, which is the same as kw tensor y, the reproducing kernel, at z. So that's precisely what we wanted. WW star plus m theta t star acting on any reproducing kernel just gives you back that reproducing kernel. So it's the identity on reproducing kernels, and so it's the identity. So that's the proof of this identity. So we have we proved the Nagy-Foias model in a special case. So the special case is, so coming back to this theorem here, now we actually know what the range of W is. Oh no, there is one more step, isn't there? Yeah. So the point is that in the pure case, W is an isometry, and so WW star is the projection, orthogonal projection on the range of W. So a corollary of this fact here so corollary, the range of W is equal to the range of 1 minus m theta t. Why don't we do this? The range, if we take the orthogonal projection, the orthogonal complement of the range of W, then it's the range of that, and that's just theta t h2 dt. And therefore, the range of W is h2 dt dt star, orthogonal complement theta t times h2 dt. So we have a very nice description of the range of W in terms of this characteristic operator function, this function here. And so we can improve our little theorem up here by saying what the range of W is H2 of d sub t star orthogonal complement theta sub t applied to H2 of d sub t. And that is the model operator. This is, or we can take adjoints here. So t star is the restriction of the backward shift to this backward shift invariant subspace of the backward shift of H2. And we can just take adjoints here, of course. So T is unitarily equivalent to the adjoint of the restriction of the backward shift. So that's the compression of the forward shift to H2 orthogonal complement theta t H2 of dt. And this is the Nagy-Foias model. In the pure case. So the case of contractions T, the powers of whose adjoint tend strongly to 0. Now, of course, that is a very special case, because for a general contractive operator that won't be true. Unfortunately, it's not really practical in a single lecture to give you the most general version. It comes about page 250 in the Nagy-Foias book. But I will state it at least. It's enough to give the flavor, I think, of the Nagy-Foias model to see the pure case. The general case is considerably more elaborate. So I think I just have time to do that. When do we finish?
10 minutes maybe.
Fine. I think that's just about the right amount of time. So now consider T a general contraction. On H. So I'm no longer going to assume that T is a pure contraction. Well, the first thing is that you can peel off a unitary. If T has a unitary part, you can peel that off and, so to speak, regard that as a well-known object. So if you look at the set of X in H, such that norm T to the n X equals norm X equals norm of T star to the n X for all n greater than or equal to 0. So you think if T were unitary, then this would be trivially true for all x's. If T is unitary on some subspace, then for x in that subspace this would be true. But if you take a general contraction T and you consider this subspace, then it might just be 0, of course, this subspace. But if it's not, then it's a reducing subspace, and t is unitary on it. So let's call that, I don't know, h sub u. So h sub u reduces t, and t restricted to h sub u is unitary. And so you can decompose h into h sub u and its orthogonal complement, and you'll get the orthogonal direct sum of a unitary operator and something that has no unitary subspace. So, so t restricted to the orthogonal complement of h sub u has no non-trivial unitary restriction. So if we're
Orthogonal complement. HU.
oh yeah, thank you. Yeah. So if we're studying a general contraction T, we might as well assume that we know everything about T restricted to h sub u. That's just a unitary operator. We have the spectral theorem and everything. The interesting part from the point of view of this theory is the part which has no non-trivial unitary part. So this is called, it is completely non-unitary. So we should study completely non-unitary contractions. So let's assume that now. T is a completely non-unitary contraction on H. And if we can get a model for that, then we will have done well. So this of course includes the pure case, because clearly a pure contraction can't have any unitary part. So it should contain this model here. So let's define the model space. H sub t. Right. So this is right. So to start with, we can write down what we've already found over here. And then we're going to take the direct sum. I think I should write it vertically like this as direct sum. Make sure I get the star right. dt, yeah, that's right. Now delta sub t, or v to the I theta, is going to be 1 minus theta sub t e to the, I shouldn't use theta, should I? Use t. Star theta sub t e to the I t. So here I'm using, so theta sub t, remember, is bounded analytic operator valued function on the disk. And so by Fatou's theorem, it will have radial limits almost everywhere on the unit circle. And so this will make sense. This is an operator from d sub t to d sub t star. So this is an operator from d sub t to d sub t for each value of little t there. Right, so there is a space of functions. This is a space of functions on the unit disk. This is a space of functions on the unit circle. But I need to take the orthogonal complement of theta t u delta t u, this space u in h2 of dt.
Remove orthogonal complement in the first sum.
Oh!
In the first column.
Ah, yeah. Yeah, thanks. That's right, yeah. Right, so there is a Hilbert space of functions. Somewhat more complicated, but nevertheless it's a sort of manageable object. And now we define I'm going to define an operator T wiggle from HT to HT by, so this is basically the forward shift operator. So T of U direct sum V. So if we take an element uv in this model space, actually it's easier to define the adjoint. So let me define the adjoint. So it's basically the backward shift applied to u. So it's e to the minus it u of e to the it minus u of 0. So that's t star, what it does to the first component, and the second component is just the backward shift. And then the theorem is similar. So I can use this same thing here. T is usually equivalent to the compression of T wiggle. So that's the adjoint of this operator to H sub T. And that is the Nagy-Foias model for a general contraction, which, as I say, it's a considerably more elaborate construction. But anyway, that's how Nagy-Foias described it. You can find a very good account in a paper by Vasily and Nikolai Nikolsky. The reference, which I don't have at the top of my head, which describes an alternative approach which gives you not only the Nagy-Foias model, but also some of these other related models that I've spoken about. Anyway, what I wanted to do in this lecture was to give you a feel for the Nagy-Foias model, which I think is approachable in the pure case, in the case that t star to the n tends to 0. In the case, if you want to understand this more general case here, that actually, I think it requires some fairly protracted study, at least it did for me anyway. And I think for the purposes of my next two talks, the next two talks will be about pairs, commuting pairs of contractions. I think it's enough really to understand the pure case. And again, I will state finally a version for the general case, but I will be happy if I can get you to understand what the result is, how the result works, not only what it is, but how one can derive it in the case of a pair of commuting pure contractions. So anyway, that's for tomorrow.
Thank you.